G'day. Young students are often introduced to the concept of fractions first through the notion of sharing, equal sharing. For example, here's a round, plain pizza. It's very important to keep it plain so there's no fights over who got more pepperoni bits on a particular slice or not. Keep the pizza plain. And suppose we were to share this equally among 3 people. What do? Well, we divide into 3 equal-sized pieces, and we call each such piece a third. A third of the pizza, a third of the pizza, a third of the pizza. And thus we're developing a notion of a new type of number called a third in this case. And we can build from that more complicated fractions. For example, we say that 2/3 is, well, exactly what I just said. 2/3, 2 copies of a third of the pizza and a third of the pizza. 2 copies of a third. Grand and good, building up more complicated fractions now. And we even notice things like 3/3, 3 copies of a pizza, 1 slice plus another slice plus the third slice, 3 copies of a third. Well, of course, 3 copies of a third makes 1 whole pizza. We're starting to develop some mathematical properties based on this picture right here. Okay, and the elementary and middle school curricula do an awful lot of work, in fact, a daunting amount of work, to develop all the intuition and mathematics of fractions through various real-world models, which is grand and good and necessary. But it's actually plagued with a particular conundrum. Here's the paradox. Even though mathematics might be motivated by real-world scenarios, in the end, mathematics turns to be much bigger and bolder than any one real-world scenario. Whoa. Math is very good, once it's been developed, at describing and pinpointing nuances in real-world examples. But the reverse is not true. No one real-world example can encapsulate the whole mathematical story. Therefore, no one real-world example can explain all the mathematics, despite what the elementary and middle school curriculum necessarily have to try to do. It's a trouble, it's a paradox. So what I want to do now that we're adults, I want to see if we can step back from this and go through all the mathematics we learned in those early grades and see what the mathematical story is behind that. We'll let go of all the real world models and just see what mathematics itself, pure math, the pure logical purity of mathematics, actually how it develops the story of fractions. And here's the amazing thing. Here's the beauty of mathematics. Everything we'll develop today, just by pure mathematics, letting go of all real world work, actually will turn out to be completely in line with all our intuition and real world modeling. It's beautiful and amazing mathematics. So it's going to be a bit of a journey. I do not recommend doing this with young students. This is now upper high school, college level work we're going to do together. But let's go through the mathematical journey of the arithmetic of fractions using pure maths to explain everything. It's going to be a blast. Okay, so what's our mathematical start? Well, mathematics is often motivated by real-world scenarios. And we just saw that pizza sharing suggests it could be very handy in the real world to have numbers of the form 1/2, 1/3, 1/4, 1/5, and so on. And that these numbers have the basic property that 2 copies of a half gives me 1 whole quantity, and 3 copies of a third gives me 1 whole quantity, and so on and so on. All right. So let's make that our mathematical start. Let's posit, as mathematicians, that we can extend our number system, our usual arithmetic system, to include a new type of number, numbers of this form, that still obey all the usual rules of arithmetic. Let me actually write this out. So I'm going to say, we posit, for each non-zero number b, there is a number written as, we'll say, 1 over b, with the property that b times 1 over b equals 1. I'm literally copying what the real world wanted us to do. Grand and good. And we also assume these numbers obey the usual rules of arithmetic, that we can addition can be swapped and multiplication can be swapped, all that usual stuff. Usual rules of arithmetic. Not that anyone can read my hieroglyphics here, but there it is. There it is in full written glory, the start of the theory of fractions. We just presume numbers like this exist. Now, there's something subtle already. I wrote non-zero because I thought about this definition for a while and I realized there's a little problem. So let's see if I can erase this part. I don't think this blue erases nicely, so sorry. Why am I assuming that b can't be 0? What's wrong with that? Why can't I have a number of the form 1 over 0? What's wrong? Well, I realize I've got a potential contradiction within my own definition if I allow numbers in the form 1 over 0. 1 over 0, if I allow that to happen, well, by definition, 1 over 0 is the number such that 0 times 1 over 0 equals 1. So if I have this, this should equal 1 by its basic definition. But if I also want the basic rules of number theory to still hold, of arithmetic to still work, we know in everyday arithmetic, 0 times the quantity should be 0. But the same token, 0 times anything is 0. So right there, I see that the existence of 1 over 0 puts us in a contradiction. We got that 1 would have to be the same as 0, which is not obeying the usual rules of arithmetic. 1 doesn't equal 0. So actually, this is the reason why I want to make sure b is not 0, because I can see that 1 over 0 is problematic with the second condition here, that the rules of arithmetic, as we expect them to hold, do hold. All right, okay, great. So that is the starting point of fraction theory. And it is convenient, and I'll just also add to this a convention. This is not a rule, this is just a shorthand. Take a over b as shorthand for a times 1 over b. So I got a bit of a squeaky marker. All right, so that's just a notational convention, which is what I did in the pizza sharing example. 2/3 was known as 2 copies of a third. So it's rather than writing 2 times 1/3 every single time, I've got a little shorthand, I'll write 2 over 3. That's just notational convention. But that's it. There's the entire story of fractions is right there, with this basic belief and that little convention for how we write things. That's it. Everything follows from one property. Astounding. So let's now march through everything and see how everything logically follows from that one idea, that one single idea. This is powerful. This is amazing. I think it's fabulously stunning. All right, let's try some arithmetic. Let's work out 3 times 2/3. All right, all I've got to work on is that basic definition of those basic fractions, 1/2, 1/3, 1/4, 1/5, and a little notational convention. In fact, I see the conventions right there, 2/3. What is that really? It's really 2 times 1/3, 2 copies of a third. In fact, actually, let me write that out. I see that 3 times 2/3 is really 3 times 2 copies of a third. Bingo. Oh, but now I look at that, I see, 3 copies of a third, 3 times 1/3. The basic property of fractions is that 3 times 1/3 would be 1. So this is really actually 2 times 1, which is 2. Bingo. 3 times 2/3 is actually 2. All right, I can now see that what 5 times 6/5 is going to be. Because what's 6/5 really? Well, it's 5 times 6/5 is really 5 times 6 copies of a fifth. Basic property of fractions, 5 times 1/5 is 1. It's really 1 times 6 is actually 6. Beautiful, beautiful. If I remember being taught in school something like just cancel out the 5s. The 5 on top and a 5 on the bottom, off they go, and bang, bingo, there's 6. But now I see why it's happening, In fact, I bet you can now prove for yourself the general rule that b times a over b is sure to be a. So that seems like a little property from school books, and there it is. I think we can now see why it's actually true from the basic property of fractions. Gorgeous. At some point in my schooling, I remember being told that a fraction is the answer to a division problem. Okay, let's see if we can unpack that. What's really going on there? First of all, what is division? We have to be clear on that. In fact, what is division mathematically? I don't want any real-world model of division. I'm doing pure mathematics here. So, for example, if I had to work out 12 divided by 3, what am I really being asked to do mathematically? Well, I guess, first of all, I'm being asked to fill in the blank to 12 divided by 3 equals, I don't know, something, question mark. But actually, mathematically, division is multiplication in reverse. This problem is really asking what times 3 gives the answer 12. There's a purely mathematical way of thinking of division, reverse multiplication. What times 3 gives the answer 12? So really what I'm doing is filling in this blank. What times 3 gives the answer 12? And of course the answer is 4. I know 4 times 3 is 12. So I say the answer here is 4. Okay. So let's think of division as reverse multiplication, the pure mathematics of that. Here it goes. Because now we'll look at 3 divided by 5. All right, so I'm being asked to fill in the blank for this. 3 divided by 5 equals something, but as reverse multiplication, it's really asking what times 5 gives the answer 3? What times 5 gives the answer 3? Well, given the work I've just been doing, I'm to know that 3/5 times 5 gives the answer 3. So actually, yes, the answer here is the fraction 3/5. The answer to this division problem is a fraction. Okay. So if I want to be a little more abstract here, what's a divided by b? If I was asked to fill in that blank, well, I'll be saying, okay, I want to know what times b gives the answer a. what times B is the answer A, and I just know that we've learnt previous section, A over B times B is the answer A. So yes, this division problem here does indeed have the answer A over B. Fractions are indeed answers to division problems. Okay. Okay, let's start playing with products of fractions. And the first example I have here is actually going to be very telling for us on how to do that. Let's work out 6 times a half times a third. All right, okay, so I see a half, I see a third, I see these numbers 2 and 3 here, which I have a feeling that 6 being 2 times 3 is going to be very helpful for us in that particular problem. In fact, let me write this out as 6 being 2 times 3 times a half times a third. Because now I can directly see by the basic property of fractions, 2 times a half is 1. By the basic property of fractions, 3 times a third is 1. This is really just 1 times 1 in disguise. It's actually just the number 1. Okay, so 6 times a half times a third equals 1. Okay, but here's what's curious. I'm to know that 6 times the sixth is 1. But that's the basic definition of 1/6, the number that multiplies by 6 to give the answer 1. So this and this fill in the same blank. And I can't help but think that must mean they're the same number. 1/2 times 1/3 must be 1/6. Okay, great, grand, and good. So it looks like I'm concluding that 1/2 and 1/3 times 1/3 and this number 1/6 are identical. Let me now just go through a little bit of extra work to clinch that. I will now prove that these have to be the same number. And I'm going to do a little bit something sneaky. This took me like a long while to think about what to do to prove that these two numbers must be the same. And the way to do it is look at this multi-product. Let's do 1/6 times 6 times 1/2 times 1/3. Okay, I can look at that two ways. I see a 6 times 6, 1 times a half times a third. So it's actually 1 times a half times a third. It's that. There's the answer to that product. Or I could say, oh no, it's really 6 times a half times a third, which I know is 1. It's a 6th times 1. I can also say this is really a 6 times 1, which is just a 6th. Ah, there it is. Yes, these two numbers that fill in the blank are identical. Beautiful, beautiful, beautiful. I've now proved that 1/2 times 1/3 is actually 1/6. Love it, love it, love it. In which case, I need a bit more space because I want to do the next examples. I bet in the next example a 4th times a 5th. Uh-oh, it's not erasing well. Okay, we're getting a smudgy board for the rest of this little segment. All right. I bet a 4th times a 5th is going to turn out to be 1/20th. I bet it's the number that multiplies by 20 to give the answer 1. So that's the definition of 1/20th. And let's check that. So let's look at this. So notice that 20 times 1/4 times 1/5 is actually, well, 20 is very nice, it's 4 times 5. It's really 4 times 5 times 1/4 times 1/5. Beautiful. Basic probability of fractions, 4/4 is 1, times 5/5 is 1. 1 times 1 is 1. 1. Yes, this number is behaving like 1/20th. Bingo, I could argue actually it must be 1/20th, they must be the same answer. I get that 1/4 times 1/5 has to be 1/20th. This is stunning. This is stunning. And I bet you could prove now abstractly for yourself that 1/8 times 1/8 is going to equal 1/8. We've just learned how to multiply basic fractions, just from the pure logic of the mathematics. Stunning. Which I think then means we're totally set to do general multiplication of fractions. For example, what's 2/5 times 3/7? All right, okay. So from pure mathematics, we can now argue that that is going to be, well, let's work it out. Well, first of all, 2/5 by definition, by convention, is 2 copies of a fifth. Times 3/7, that's 3 copies of a seventh. I'm just spelling out what that shorthand means. All right. So I've got 2 times 3 times a fifth times a seventh. I know 2 times 3 is 6. I can actually do that one. And then I've got times a fifth times a seventh. And we've just figured out how to multiply basic fractions. Oh, it's 6 times 5 times 7, 1/35. That's 6 copies of a 35th. This must be 6/35. Whoa, whoa. And it looks like I've just multiplied those numerators and multiplied those denominators as I was taught to do in school. In fact, I bet you can also prove abstractly right now that A beths times C deths is sure to be AC over BD. I bet you can give a nice little abstract proof of that in general. This is beautiful. Everything's falling into place. Okay, the fun continues. let's now show that 4/6 is really the same as 2/3. All right, so all I've got is the basic definition of what 4/6 means, 4 copies of the 6th, and all the work I've done so far. I bet I can show it's the same as 2/3. Here goes. 4/6 is 4 copies of the 6th. Great. Okay, we were just thinking about 6. I do know that's actually 1/2 times 1/3. And actually 4 is nice, there's a 2 times 2. It's actually, well, it is 2 times 2, now I've got times 1/2 times 1/3. That's very handy because now I can use the basic property of fractions. I get 2 times 1 times 1/3. 2 times 1 times 1/3 is that, and that's 2 copies of 1/3. Yes, it is indeed 2/3. Okay, I've just shown that the fraction 4/6 is really the fraction 2/3 in disguise, and people call those equivalent fractions. In fact, I bet in general I can copy exactly what I just did there and just prove that AK B-kths is the same as A bths. Okay, why am I trying to say this out in words? I don't know, but here goes. Here's how I'd prove this in general. AK B-kths is by definition AK copies of the fraction 1b-kth. All right, well AK, two letters next to each other like that really means multiplication. That's really A times K times. And we just know that actually I can think of this as the product of 1b times 1k. So I know that product would be 1b-k. Great, everything's hanging together. What do I like about this? I see a basic property of fractions right there. K times 1k is actually 1, so I get 1 times A times 1 over B. This is just A times 1 over B, which by convention is indeed A over B. So yes, we've now proven the equivalency of fractions. If a fraction has a common factor, if you like, in the numerator and denominator, we can just cancel out. I was taught to just cancel out and reduce it that way, I guess is what I was told. Or you go backwards. If you're given a fraction, you want to like scale everything up, the top number up by a particular number, and the bottom number up by the same number, so long the numbers are the same, it won't affect the value of the fraction. For example, here goes, I'll do it both ways. Here's which color, I'll do it in green. 10/15. I'm being taught in school to recognize that as 2 times 5 over 3 times 5, in which case I can just cancel out the 5s and say it's actually 2/3. Bingo, I've now proven I can do that. I've also proven that if I like, I can now scale this up. I want to multiply the top by 7 and the bottom by 7. Feel free, as long as these numbers are the same, it won't affect the value of the fraction. So I can say this is really the same as 14/21. Okay, everything I was taught in school about cancelling common factors and scaling up by top and bottom by the same number is mathematically solid and good. We are golden. Okay, let's now divide some fractions. But before we start, let me just notice that actually a fraction in and of itself is an answer to a division problem. The answer to A divided by B is the matching fraction A over B. So, given a division problem like this one, 6/11 divided by 5/7, the answer just has to be the fraction that goes with it. Namely, the fraction with 6/11 on top and the fraction with 5/7 on the bottom. Whoa, whoa. That's the answer. It's a pretty scary looking answer. I don't really have a feel for what that is. So now the question is, can I make that answer look friendlier, more comprehensible? And the reason why it doesn't look comprehensible to me right now is I've got fractions within fractions. Ick. But, I know I could probably fix it up. For example, I don't like 11ths as part of my numerator. So what I could do by equivalent fractions is scale the top and bottom each up by a factor of 11. I have a feeling that's going to then make the numerator nice. Also, by choosing the same numbers by scaling the top and bottom, it's not going to change the value of the fraction. Still the same number. All right, so let's actually work this out. So this is now going to be what I've got. I'll tease out the numerators. Really, 6/11 is really 6 times an 11th, then times 11. Great. And on the bottom, I've got 5/7. It's really 5 times the 7th, and that gets multiplied by 11 as well. So the numerator is indeed nice. 11 times 1/11th, that's 1, basic property of fractions. 6 times 1 is just 6 for the numerator. Lovely. But the denominator is actually still icky. 5 times the 7th times 11. Okay, but I know I can scale the top and bottom up by the same factor and it won't change the value of the fraction. If I don't like that 7th in the denominator, let's multiply by 7 on the bottom and multiply by 7 on the top. Nothing's changed, but I have a feeling it's going to make things much nicer. Because now I can see 6 times 7 on the top, and I can see, well, I've got 7 times 1/7, basic property of fractions, that's 1. So it's really 5 times 11 times 1, it's just 5 times 11, that's 42/55. Beautiful, grand, and good. All right, so I've just divided these fractions. And most people notice that 6/11, 6 on top, 11 on the bottom, I've kind of got that there. And people do notice that 5/7, I've kind of got it here, but it's kind of an upside down version of it. All right, I bet you can prove in general that that pattern is true. If I take A bths and divide by C dths, the answer really will be A on top, B on bottom, D on top times D on top times C on bottom. Okay, bingo, I bet you could prove that by following exactly this technique. But the reason I'm really putting out this right now, because school does something strange. They say to work out A divided by B, A bths divided by C d, just keep, change, flip, which is deeply mysterious. What they mean by keep, change, flip is keep the first number the same, A over B, change the division to multiplication, and flip the second fraction. Instead of C over D, make it D over C. Whoa, and then compute that product. Well, if you compute that product, what do you get? You get A times D on the top and B times C on the bottom, and lo and behold, it actually does match that. But keep, change, flip is really weird and mysterious. It is often told to students just out of the blue, here's a random thing you can do to divide fractions. Okay, I'll just do this random thing. But here's the point. You can prove that random thing. It has actually mathematical grounding and structure to it, and it's actually mathematically correct. It is the right thing to do in the end as a computation, but now you can see why it's the right thing to do. This is indeed powerful. Okay, the play continues. Recall that 1 bth by definition is the number that fills in the blank to this. B times 1 bth equals 1. Okay, that which multiplies by b to give the answer 1. So 1/2 times 2 equals 1, 1/3 times 3 equals 1, 1/4 times 4 equals 1, and so on. In fact, you may have noticed at the very beginning of today, I only ever spoke of the fractions 1/2, 1/3, 1/4, 1/5, and so on. I skipped over the fraction 1/1. So let me ask right now, what is 1/1? Okay, well, if I follow this definition, 1/1 is the number that fills in this blank. It would be 1 times something equals 1. 1/1 goes in there. But actually, I know the number 1 also fills in the blank. So 1/1 fills in the blank, 1 fills in the blank, they must be the same number. Whoa, 1/1 equals 1. And in fact, if you think of division, like we said that fractions are answered division problems, 1 divided by 1 is 1. Okay, it's 1. Lots of ways to think about this. But there it is, 1/1 is 1. So what's 7 over 1? 7/1. Well, actually, I can be a little more quicker here, because 7/1 by definition is 7 copies of 1/1. We just figured out 1/1 is 1, so that's 7 copies of 1. 7 times 1 is 7. In fact, I bet you can prove right now that A/1 is sure to be A by using exactly that same argument. So there's a general principle. If you want to put a number over 1, feel free, it won't change anything. Okay. Okay, it might seem a little strange that I left addition and subtraction of fractions to this late stage of our development. Well, the reason I did that is because actually addition and subtraction is quite unnatural for fractions. Remember, fractions are answers to division problems. They're naturally connected to division. And since division is reverse multiplication, they're naturally connected to multiplication as well. There really is no addition and subtraction in the story of fractions per se. But you can get to that nonetheless. You can bring those operations into the story of fractions nonetheless by being sneaky. So I have to be sneaky here to get the story of addition in. For example, let's see if we work out 1/2 plus 1/3. I know the answer is going to be 5/6, but I want to see if I can get 5/6 using only the tools we've developed so far. Okay, now the sneakiness I'm going to employ right now is what we just learned. They can put any quantity over 1 and it's still the same quantity. So I'm going to think of this as 1/2 plus 1/3 all over 1. Which is very strange because I've now got fractions within fractions. And no one really likes fractions within fractions. So my question is, can I fix it up and make it look friendlier? And the answer is yes. If I don't like the half here for starters, I could actually multiply the top by 2. I think that's going to be very nice for that particular half right there. But I can't just willy-nilly multiply the top by 2. We've learned I better multiply the bottom by 2 as well. Scale the top and bottom up by the same number, it won't affect the value of the fraction. Great, so now I can see this is going to be 1/2 times 2, that's 1, plus 1/3 times 2, that's my numerator, and I'll get 1 times 2 on the bottom, that's 2. All right, I've still got fractions within fractions. I don't like that third at the top. The way I can get rid of that, help myself with that one, is multiply the top by 3, and to keep it balanced, multiply the bottom by 3 as well. Because now I can see the numerator is going to be 1 times 3, that's 3, plus 1/3 times 2 times 3. 1/3 times 3 is 1, 1 times 2 is 2, that's 3 plus 2 on the top, and 6 on the bottom. There indeed is 5/6. Out came the addition of those two fractions. Beautiful, grand, and good. A little bit sneaky to get there, but I got there. You can bring addition into the story of fractions by this clever, clever little move. In fact, let's do a more complicated example. Let's do, oh, my marker's not going to erase very well. All right, it's going to get messy. But let's do 2/3 plus 3/10. Let's use this technique and see if we can figure out the answer to that one. All right, so first of all, I'm going to be sneaky and write it over 1. In fact, that's a very good strategy in general. If you've got a quantity you don't know what to do with in fraction world, try putting it over 1 and then multiplying the tops and bottoms by clever things. All right, so this is really equal to 2/3 plus 3/10 all over 1. But let me actually really tease this out. That 2/3 is really 2 copies of a third plus 3 copies of a tenth all over 1. All right, okay, so I don't like fractions within fractions. I don't like the thirds on the top. Let's multiply the top and bottom by 3. That doesn't affect the value of the function. The fraction is still good. Whew. So on the top, I see I've got 2 times the third times 3. That's 2 times 1. So I just get 2. Plus I get 3 times the tenth times 3. So I get 3 times the tenth times 3 all over 3. All right, now what? Well, I've still got fractions within the fractions. I don't like the tenths at top. Let's fix that up by multiplying top by 10 and bottom by 10. So now I can see it's going to be 2 times 10 is 20, plus 3 times 3 times 1. That's 3 times 3, that's 9. 20 plus 9 all over 30. Bingo, it's 29/30. Grand and good. All right, so I can add general fractions now. Okay, it's not particularly fun, but it's totally doable. It's within our theory of mathematics, there it is. I bet I can subtract fractions as well. In fact, I bet the work is going to be basically the same. So I'm going to be a little bit naughty and see if I can just adjust this answer to be this answer. So let's do this. Let's put this line here and write equals 2/3 minus 3/10 over 1. Minus 3/10 over 1. Let's tease that apart. 2/3 is really 2 times 1/3. Take away 3 times 1/10. I'm going to multiply the top of 1 by 3. Perfect. I still get 2. Yep. And I'd get take away 3 times the tenth times the third. Yes. And then what happens? I multiply top and bottom by 10. I will get 20, and I'll get take away. Yes, take away 9. 3 times 1, but all take away. Great. And I see now the answer is going to be, it's going to be 11/30. So subtraction is actually no different from addition right here. Wow, there it is. It's all coming together. And I bet I could write a general addition rule and subtraction rule. Probably won't look pretty, but I bet it will match everything I was taught to do in school. This is looking great. In fact, actually, let me go a little bit further. What I was taught in school, okay, now this is going to be hard. How am I going to do this? What I was taught in school was actually to add fractions by putting things over a common denominator. Does that ring a bell in your world? And then I was taught, well, if you've got common denominators, you can just add the numerators. That is, I was taught that in general, a nths plus b nths is sure to be a plus b nths. I bet you can prove that right now. What I'll do is I'll probably start with that and put it over 1. Putting over 1 is really cool. A nths all over 1. Now I bet you can see what to do with that to see it's really the same as that answer. In fact, putting over 1 is such a good trick. Let's actually redo one of our earlier problems. Let's compute 1/2 times 1/3 again, the product. Let's compute 1/2 times 1/3. I know we showed that was 6 earlier on, and we had to go through some argument about proving uniqueness, but actually we can do it right now without getting into philosophical troubles. Here goes. 1/2 times 1/3, put it over 1. Put it over 1. Sounds good. Now it's very compelling to multiply the top by 2 and the top by 3 and keep it balanced by doing the same thing for the bottom. Multiply the bottom by 2 and the bottom by 3. Because what do I now get? 1 times 1 on the top, 1 on the top, and 6 on the bottom. Whoa, whoa. This move to put things over 1 can be really, really handy. Loving it. A mixed number is just a whole number and a fraction added together. For example, 2 1/3 is literally what I just said, 2 1/3. 2 1/3 is 2 plus 1/3. Just society has agreed not to write the plus sign. A little annoying, but there it is. So 5 3/4 would be 5 plus 3/4. That's all a mixed number is. All right, so let's do some mathematics of mixed numbers. And again, I bet it's going to match everything I was taught to do back in my school days. For example, let's say we write 2 1/3 as a single fraction. All right, so the technique I like to do, if I'm not sure what to do, put it over 1. So 2 and a third is really 2 and a third over 1. But let's be really clear, that's really 2 plus a third over 1. Let's write out all the mathematical details. And now it feels compelling. I see a fraction with a fraction. I don't like it. Let's multiply the top and bottom by 3. Just feels the natural thing to do. In which case I see I've got 2 times 3, 6, plus a third times 3. The reason I did this, 1 all over 3. And I now see it's the single fraction 7/3. I bet I can convert any mixed number into a single fraction following this technique. All right, great. And I bet we can go in reverse. For example, let's say we can write 17/5 as a mixed number. So as a whole number plus some fractional part. All right, okay. All right, so I can see in this one that I'm going to be dealing with fifths. And I've got to somehow get whole numbers into this story of 17/5. And I do know I can get whole numbers from fifths in some sense by using the basic property that 5 copies of a fifth would indeed be 1. So what I'm going to do is I'm going to see if I can get as many instances of this going on as possible. All right, so let's play with 17/5. What do I mean? 17/5. Okay, this really is 17 copies of a fifth. Let's be very clear right there. Now I'm going to get as many 5s as I can out of the 17. I'm going to think it says 5 plus a 5 plus a 5. That's 15. I guess 2 more left over. That's as much as I can do. Because now I can start getting some whole numbers out of this. I get 1 plus 1 plus 1 plus 2 copies of a fifth. And that is actually 3 plus 2/5, which is the mixed number 3 and 2/5. There it is, bingo. And I bet I could use that technique to turn any improper fraction, one with a numerator bigger than the denominator, into a mixed number if I so desired. Okay, this is beautiful. I think it's covered most everything I was taught to do with fractions in school. This is grand. Yeah, as I just said, I think we've now covered everything to do with fractions. It's all grand, it's all mighty good. Now admit this was actually mighty fast. This was a very fast overview of it. That's fine. If you hung on, brilliant, thank you. I speak fast, I do math fast, but there it is. There's all the math. And we've shown that every technique you were taught actually has mathematical meaning, it's mathematically grounded, and it's logically correct. Now, I've gone through all this stuff. I'm not saying that you should actually do fraction arithmetic the ways I've done today. The point today was to show that everything you were taught to do is actually mathematically grounded and is mathematically correct, so feel free to use your old techniques. That's grand. Now that we know they're good, use them. No need to do all the work I've just been doing. However, if I have actually skipped over some technique you were taught, it's now beholden upon you to try to prove it using the techniques of today. Because then once you've proven it for yourself, then you know you can legitimately use it, and that's good. This is powerful. Mathematics is bigger and bolder than any real-world model. Just the math alone has actually explained everything. Even though each individual model you learn in school can explain some aspect, no one model explains the whole story of fractions. It's the math that explains the whole story of fractions. And it's stunning.